Hi, and welcome to Kitchen Math, where we cook, hear the sizzling chicken, and do math all at the same time. Tonight's lesson is average rate of change. So we're going to discuss how a function changes along a curve over different domain intervals. Okay, so let's take a cubic function. We know it's cubic because its end behavior is in opposite directions, and it has three real zeros, three roots of the function, so it is a cubic function. Now, when we discuss an average rate of change, you always need to discuss it in terms of two domain intervals. So when we look at the curve, we notice that it is increasing, followed by a maximum point. It decreases on this side, followed by a relative minimum point, and then it begins to increase again. So if we take any domain interval along this curve, we can evaluate what the average rate of change is between any 2 points. So take these two red points here. If I talk about the average rate of change, how this function changes from this value to this value, I could think of it as connecting the points with a line, and think of it in terms of the change in the y values divided by the change in the x values, which is also the slope. So an average rate of change is similar to finding the slope, but because we're on a curve and not a line, the slopes will change according to where I am on the curve. The average rate of change here would be a positive since my curve is increasing. If I evaluate the average rate of change and get a little closer here to this point and draw another secant line connecting those two, that slope is going to be different. If I get even a little bit closer and draw another secant line, that slope again will be different. So as the line moves through the curve, you'll see that each time I take a different domain interval, my rate of change will be different between those 2 points. All the way through the curve, it's going to be different. Now, when the curve is decreasing, this average rate of change is going to be negative because the slope of this line connecting those 2 points, which is the secant line, is negative. Now, this important concept comes into play in both calculus and physics. So if you're currently taking physics with Algebra 2, you can relate this to the velocity graph. So keep in mind, the velocity of a function is the ratio of the distance divided by the time. If my x-axis was my time and my y-axis stood for the distance, the ratio of the distance to the time is what's known as the velocity. In calculus, if we bring these points together that I'm evaluating, the domain interval, closer and closer and closer together, then we get close to what's known in calculus as called the instantaneous rate of change, which will then lead you to the concept of derivatives. And the first derivative of the function corresponds with the velocity of the function. So this has a lot of application to mathematics in both calculus and in physics. Now, if we bring these points to closer and closer and closer, we move this point to this point, we are decreasing the value until we get infinitely close. And that is called taking the limit as the limit is approaching zero. So as we're decreasing this value in between, we're going to get a better approximation of the derivative of the function. Okay. So, an average rate of change, then, to recap, is how the function changes between any given domain interval on the function. Now, if we take a linear function, all this becomes quite easy because a linear function if I take the change in the y, divide by the change in the x's, along any points along this line, it's going to remain constant. In a linear function, the average rate of change is known as the slope. But in a curve, we can't talk about it as being the slope because we don't have a constant rate of change. It changes each time we're at a different point on the function. Okay, so let's talk about how we calculate it. So say I have this function again. This is a cubic function with one real root and two complex roots. Notice it does not touch the axis at that point. And I want to calculate the average rate of change between, say, this point here and a point up here. Now I'm just going to arbitrarily call this -1, 3, and I'm going to call this point 2, +1. Okay? Now the average rate of change, since it is kind of thinking of it as the slope of the secant line that passes through these points, I'm going to think of it as the change in the y over the change in the x. But we don't write it that way. For the average rate of change formula, we write ARC equals, I abbreviate average rate of change ARC, some teachers abbreviate it ROC. It equals the function value at one point minus the function value at the other point divided by the x's subtracted. Okay, so f at b, we're going to call this point b, minus f at a, I'll call this point a, and then divided by b minus a. Okay, so f at b is the y-coordinate of the point b, which is 1. F at a is the y-coordinate of the y value of the a coordinate, which is 3, divided by the x coordinate. B x coordinate is 2 minus a's x coordinate, -1. This value, 1 minus 3, is -2. 2 minus -1 is 3. And so the average rate of change is -2/3 in the interval between -1 and 2. Okay. All right, so now what happens if I don't have a graph and I actually have a function that I want to calculate the average rate of change for? So in this type of problem, I don't have a picture of it. I'm only calculating it based on the function that's given. So here's a function. It's quadratic. It's degree 2. It's translated 3 units down the y-axis. And so again, recalling our previous lesson on even and odd functions, this is an even function with symmetry about the y-axis. And now I'm going to calculate the average rate of change on the interval -2, 1. Okay, so when x is -2 to x is 1, I want to know what is the average rate of change. How is this function changing? If I were to draw the secant line between these values, between those coordinates, what would the slope of that line be? So to do this, you take the function value at 1 minus the function value at -2 divided by 1 minus -2. Notice here that this value, x, will line up with this x value, and this value here will line up with that one. This is actually, f at 1 is the y value minus the y value, so this is essentially delta y, and the x value minus the other x value is delta x, the change in y over the change in x. Okay, so substituting the value 1 in for the function, I get 1 squared minus 3, or -2, and substituting -2 in for the function, I get -2 squared 4 minus 3 is 1. And the difference of the x's becomes 1 plus 2, or 3. And that becomes -2 minus 1, or -3, divided by 3. So the average rate of change for this function on that interval is -1, which tells you what? It tells you that on that interval, the average rate of change, meaning the slope, it's decreasing on that interval. The function is decreasing on that interval because it's a negative. Okay, we could do the same thing with any function. You merely take the interval values and you plug them into the formula f at b minus f at a divided by b minus a. Okay, so let's take something very simplified. If I have another function, g at x equals negative 2x plus 1, and I want to calculate the average rate of change on the interval negative 2 to 1 again, I'm going to use my ARC formula, f at 1 minus f at negative 2 divided by 1 minus negative 2. Now, knowing that this is a linear function, you should already know what the answer is. So think to yourself, how would I know? What clue do I have, given that it's linear? And what do I know about the equation of a linear function? So keep that in the back of your head as we're calculating this. F at 1 means I'm substituting the value 1 in for x. That becomes negative 2 plus 1, which is negative 1. I'm substituting negative 2 in for x. That becomes 4 plus 1, which is 5. The denominator, 1 minus negative 2, is 3. And if I take negative 1 minus 5, I get negative 6 divided by 3. And negative 2 is my average rate of change. Now this negative 2 is no surprise, or it shouldn't be a surprise, because since it's linear, what do we know about linear functions? The average rate of change remains constant. And we have the coefficient of the linear term, negative 2, and this negative 2 are the same negative 2. Basically the slope of the function when we're dealing with an average rate of change. Okay, so you're going to get problems where you have a graph and you have to calculate the average rate of change. Average rates of change, as the function gets steeper, the average rate of change will increase. As it becomes less steep, the average rate of change will get less steep. So if you take a function and you've got something like this, and I'm looking and I'm saying, well, where's the steepest part of this function? Where is the average rate of change going to be the greatest? It's going to be the greatest on an interval where the function is the steepest. So it's not going to be the greatest between these 2 points. It'll be greater between these 2 points, or between these 2 points. So think of it as drawing that secant line, connecting the 2 points, and then looking at the slope of that line. What is that slope doing? Is it increasing? Is it decreasing? Is it steep? Is it approaching a horizontal line where that would be 0 slope? And those are different clues that can help you know that you're on the right track. Okay, you'll be looking at graphs, you'll be looking at functions, plugging in values, or table values where you calculate the change in the y's over the change in x's. Okay, that's all for average rate of change. Have a good night. It's time to get my dinner.